All right, we are going to get started with Unit 3, Lesson 1. And this lesson and unit really is all about exponential functions. Okay, exponential functions look like this. This is the form of all exponential functions where A is the initial amount and will also always be our y-intercept. And we'll talk about why that is in a minute. And B is the base. And the base determines if we have exponential growth or exponential decay. If b is greater than 1, the function will be exponential growth. If b is less than 1 but greater than 0, we never have a negative base. We always have positive values for b. So if b is between 0 and 1, we'll have exponential decay. Okay? So why is the y-intercept always a? Well, let's just imagine for a second I plug in 0 for x. If I have a times b to the 0, regardless of what these numbers are, it doesn't matter. Anything to the power of 0 is 1. And of course, anything times 1 is itself. So regardless of what a and b are, a will always be the y-intercept. Okay, so I'm going to draw two graphs here. One of them is going to be for exponential growth, and one of them is going to be for exponential decay. So right here, I'm just going to mark A. And if I have exponential growth, my graph is going to look like this. If I have exponential decay, the graph is going to look like this. Okay, so this is growth. This is decay. Now, you may or may not have seen a graph like this before. Hopefully, you've at least seen something that looks something like this. But one important thing to note is that this function, whether it's growth or decay, will not touch the x-axis. Okay, so let's imagine I plug in negative numbers. Okay, so again, we'll go to our very generic case here. Even if I have a negative exponent, let's say I have a times b to the negative fifth. What do I do with negative exponents? Well, it doesn't actually turn into a negative number. It turns into a fraction. It gets flipped. So when the x values get negative, our numbers get really, really tiny. And of course, when x is a positive number, our numbers are going to get really big really fast. So there are no x-intercepts for either growth or decay. Domain. Domain is all real numbers or negative infinity to infinity. However you want to write it is fine with me. This graph is going to continue to the left forever and right forever. I can put any number I want in for x. Range. And this applies for both growth and decay. Range, graphs go up forever, and interestingly, they do go down forever. However, there is a limit, right? We just talked about this, how we're never going to get negative outputs. And in fact, we're never going to get an output of 0. Our graph will keep getting closer and closer and closer to 0, but will never actually be 0. So the range is 0 to infinity. Next thing, so we talked about growth versus decay. We talked about domain, range, y-intercept, x-intercept. There are no x-intercepts. Increasing or decreasing. Exponential growth is always increasing. There's never a moment where it's decreasing. And then the opposite is true for decay. Decay is always decreasing. Okay, let's talk about end behavior. End behavior. End behavior means that I'm going to do the limit as x goes to infinity. And I'm also going to do the limit as x goes to negative infinity. And this one is different for growth and decay. So we'll look at the growth graph first. So as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to 0. Okay, f of x goes to 0. It's going to get closer and closer to 0. And these are basically flip-flopped for decay. As x goes to infinity, the y values get closer to 0. And as x goes to negative infinity, we go to infinity. Okay, so good overview, reintroduction to everything about exponential functions. Now let's do some stuff with them. So example 1, it says evaluate each function at the indicated value of x. So our first one is f of x equals 2 to the x. So if x is 3, I'm just going to have 2 to the third, which is 8. 2 times 2 times 2. All right, what if x is negative 2? We just talked about this not too long ago. If I have a negative exponent, that means I flip the fraction, right? And this is not going to be a negative answer. It's just going to be a smaller answer. So, what if x is negative 3, right? That doesn't make it negative. It just makes it smaller. That's why it gets closer and closer to 0. Okay. Now we have a new function, g of x. X equals 0. Guys, we should already know the answer to this without having to plug it in. 4 to the 0. Hey, make sure you're doing PEMDAS. Some people like to do 3 times 4 first, but we got to do our exponents first. Anything to the power of 0 is 1. 3 times 1 is 3. Ooh, fraction. Everybody's favorite. 3 times 4 to the 3 halves. What does it mean to raise something to the 3 halves? Power over root. Raising something to the 3 halves is the same as taking the square root and cubing it. So square root of 4 cubed. Square root of 4 is 2. 2 cubed is 8. So I got 24. Okay, let's sketch some graphs. Now, we're just going to do a sketch. We don't have to do anything crazy as far as, plugging in points and that sort of thing. But there are a few things that you should have correct. One of them being the y-intercept. I know right away that this graph is going to hit the y-axis at 3. And I know here that h of x is going to hit the y-axis at 2. Okay, the next thing that you need to be able to correctly identify is the fact that g of x here is exponential growth because b is greater than 1. And here, h of x is decay because b is less than 1. And then you draw your graph appropriately. Your graph should also never hit the x-axis. Okay, I'm not looking for anything too intense. I'm not expecting you to plot every individual point, but you should have a general sense of what the graphs are going to look like and important characteristics. Okay, let's flip the page. Example 3, determine formulas for the exponential functions g and h whose values are given in the table below. Okay, so just a reminder, when we write an exponential function, I need to know what a is and I need to know what b is. Okay, so a is going to be our initial amount. And for g of x, a is 4. And for h of x, a is 8, because that is what we get when x is 0. Okay, that's our y-intercept. B is the rate. Basically, what do I have to multiply by to get my next value? Okay, so if I look down the table, what's happening? My values are tripling every time, which means that B is 3. So I would say g of x is 4 times 3 to the x. Okay, now what's happening to h of x? The values are actually getting smaller, which tells me that we have exponential decay, right? We're dividing by 4, which really means we're multiplying by 1/4. So h of x is 8 times 1/4 to the x. Okay, last thing I want to talk about is e. E is this crazy number. Okay, e is kind of like pi in that it is this constant that we use. It's an irrational number, right? It's this decimal that goes on forever and ever and ever. And instead of using the number to represent it, we use this symbol. And in this case, we use E. It was discovered by this guy named Euler. So sometimes it's called Euler's constant. And I know that doesn't look like Euler, but I promise that's how you pronounce it. He was a famous mathematician. A lot of the stuff that we know about mathematics today is because of Euler. Okay, so E is approximately 2.71828, and it keeps going. And if you can just remember 2.71, that's totally fine. Okay, now in class, I will kind of explain to you where E comes from, but it has to do with growth and change. And so E always comes up with exponential functions because exponential growth, we talk about how things are growing. A lot of times, and you'll see this in the next lesson or even down below, right? We talk about interest. Interest is how our money grows. In the next lesson, we'll look at population growth. And E is this number that is very much related to growth. So e to the x is just an example of another exponential function. Okay, it just is that our base is 2.7. Okay, but we don't write 2.7, we just write e. Okay, so if it makes you feel better to think of it as 2.7 to the x, think of it as 2.7 to the x. But it really is just, it would look just like any of the other exponential functions we looked at. Now, what's my initial value? Technically, there's a 1 there in front, right? And anything to the power of 0, including e, is 1. Okay? Anything to the power of 0, including e, is 1. Okay, so the example says, use a calculator to evaluate the function f of x equals e to the x at each indicated value of x. So I'm just going to show you where you can find e on your calculator, and then we'll punch these in. Okay, so we have x is -2, so I need to do e to the -2. So you should see the division symbol, and if you don't have a calculator, pause the video and grab a calculator. Right above the division symbol, there's an e there. That's what we want. So I'm going to press the blue second button and then e to the -2. Now, this is not going to be a negative number. Remember, this actually means 1 over e squared. Okay, so why don't you pause the video and try the other 3 and see if we get the same answer. All right, here is what I got for my remaining answers. We are going to leave compound interest for lesson 2. It goes better with that lesson. So we're going to leave that for now. Your homework is on pages 3 and 4. So numbers 1 through 24. So you have a little bit of stuff on exponential functions as well as some review, as always. All right, we'll see you for the next one.